Welcome, everyone. This is another Epicure webinar from the Epicure webinar series. And today we're going to have two people from the Jülich Supercomputing Center, and they are going to talk to us about the upcoming first exascale computer in EuroHPC, Jupiter, which will be in Jülich at JSC. Um, and our speakers are Jolanta Zupa and Junqian Chu, and they are both researchers at JSC. They are HPC specialists, and they will be the ones guiding us into the the first impressions of Jupiter, which I guess most of you are very excited about. And what makes me think that is that we reached the record of registrations for a webinar. So I guess this topic is very hot. So I hope you enjoy it. And throughout the presentation, you can interact with us using the chat. The Q&A session will be at the end. We ask for you to keep your microphone muted during the presentation just to prevent some noise. And this session will be recorded and in soon it will be available on the Epicure website so you can rewatch it or send to someone who didn't register. So it will be available to watch later. So with this, I thank the speakers and I will pass the ball to them.
Awesome. Thank you very much for the kind introduction. I'll share the slides. I just want to point out that while I'll be sharing the slides, I will not see the chat throughout the whole presentation. But if there are any quick questions, maybe my colleagues, particularly Junxian Chu, who will give the second part of the talk, if you see something, you're welcome to answer already. So let me do the sharing. All right. So I hope you do see the slides in presentation mode now. Yes, from someone?
Yes, indeed.
Yes. Awesome. Thank you very much. Great. Then let me start this presentation with just quickly showing you a satellite view of the little town of Jülich, which is in the very west of Germany, close to the border of Belgium and Netherlands, in the midst of very rural place and brown coal mines. And next to this little town of Jülich, there's one of the largest European research centers, the Research Center Jülich, or in German Forschungszentrum Jülich, abbreviated FZJ. One of the institutes of Research Center Jülich is the GSC, the Jülich Supercomputing Center. And previously, at least one side of our building, when they were looking out of the windows, they were looking at a meadow. But approximately half a year ago, the view changed to show for many, many months just a simple base plate in preparation for the upcoming exascale computer Jupiter to be installed there. And in the past months, installation has ramped up, and currently the view is as follows. So here you see pretty much all the containers that will host or which will contain all the hardware for this exascale machine. So this is a novelty that for the first time at GSC, an HPC system will be hosted in containers and not in a building of its own. So this is very interesting to see. So all the hardware is, oh, we'll come to the hardware one slide after. So before that, just to give a brief history of the Jülich Supercomputing Center. So we are hosting HPC machines already for quite a while and have an experience, always growing with the time. The two main messages to take away from the slide is that there are two types of HPC machines that we are hosting. One is GPU heavy, the other is CPU focused. So the ones that are CPU focused are called cluster. The ones that are GPU machines are called booster in the end. So currently our main production systems are JUWELS cluster and JUWELS booster. Jupyter that is installed is JUWELS booster. There is a JUWELS cluster that is supposed to come a bit later, but currently we have the JUWELS booster. In the slides, it is abbreviated simply as Jupyter, but please note that the machine that we're having is the GPU one, the Jupyter booster. And the second one is because we're in Jülich, we have a funny naming convention that all our machines start with the letters J and U, which explains why this one is called Jupyter and the previous one is JUWELS, and before that, Eureka, and so on. All right. The Jupyter booster, when it's fully operational, is supposed to hit 1 exaflop of performance, and it will have around 6,000 compute nodes. The major thing is the hardware out of which it will consist. So every node will consist of 4 NVIDIA Grace Hopper superchips. One superchip consists of one Hopper H100 GPU, which has 96 gigabyte of memory, and the Grace CPU that consists of 72 ARM cores with 128 gigabyte memory. So the total memory per node will be 480. The total number of cores per node will be 288, so 72 times 4. The total number of GPUs will be 4 per node. This information is needed for you to plan, design your jobs, but also to calculate the compute hour requirements for your computes. We'll come to that a bit later. So below that is a diagram of the design, how a node consisting of 4 of those super chips look like. I guess the known novelty of the Grace Hopper is the unified memory between CPU and GPU. But in the second part, my colleague will share more insights about working with this hardware actually for our scientific applications. Below, I posted you a link to our website where, again, all the specifics are described and you can read upon them if this is when this becomes relevant for your actual development or running your own applications or codes. So yes, now the slide to which I was jumping ahead, which is like we saw those nice like containers on the slide, and actually all the hardware for Jupyter Booster is there now. So those containers that you saw are also called AT rooms, and all 8 out of 8 are already there now. There are all the power substations, 15 out of 15. There are diabatic towers, the ones that are needed for cooling the systems, 14 out of 14 are there. All the racks, 125 out of 125. The cabling, and 2 of the storage system, the Exastore and the Exatape, are all already there. This is also nice. One storage system, the Exa flash storage, is still in progress, but we are almost complete with all the hardware. Here I show you a couple more pictures. So in the top left slide, you see one of those containers that was delivered with the racks in there. So the black stuff inside the white container are the racks. I believe a container will host 2 cells. That means 10 racks and 960 nodes, if I'm not mistaken. And oh no, sorry, 1 cell with 2 rows. Yes. So the top right picture shows you the Exa storage. The bottom left, the cabling behind that, and the bottom right, I believe, some of the login nodes. So this is how all this nice hardware looks like. What about software? This is actually also like already very, very advanced, which is very nice. So the management networks are completed, the login node preparation is done, the integration with Slurm routines and done, the integrations with other site routines, I'd say like it's largely done. And with the system is also fine, but largely I'll show you on the next slide. And things that are in progress are the following. So one is called like stabilizing, which is the delivered compute nodes that have been already like connected and stuff are consecutively added to operation, which needs for a lot of things to scale up, like the electricity delivery, the cooling, and so on. So they're continuously like added to the system, so it's scaled up, and the team that's responsible for that checks that it's all like stable and there are no bottlenecks and nothing is overloaded. And with this onlining and stabilizing phase, there also comes like testing, more from the software side, which is also performed now. In approximately a week's time, it is expected that early access can be given to the Jupyter system. So the first people that can come online are from the so-called UREAP project. This was the early access program for which you could apply about a year ago, offered by the GSC. So those people had been already extensively testing the applications on the test system JEDI that we'll also talk about a bit more in the progress of this lecture. And so they will migrate there first to also test the system. And a couple of weeks after that, we expect that also first access can be established to like a broad spectrum of users through offering GCS test projects. Also talk about this in more detail in upcoming slides. So besides all the hardware and the software, when you have a project at GC or run your computations here, this comes with a whole package of extra goodies to which you have access. So a lot of extra tools and portals that are running. And this is why I said largely before on the last slide, because there are still some things with connecting the functioning hardware and software with also, or integrating with the full functionality of these tools is ongoing. So I believe the most important one is the UDOR. So every user that comes in our systems has an account there. And through this, you can manage both your personal space as well as for PIs, the projects and access to resources. Also accounting of the compute time that you have used is something that is displayed through the UDOR interface. You also have access to another tool that is called ContView through UDOR that shows you a timeline of resource usage and whether you are in the time plan or maybe close to run into a bottleneck with some of the resources, a very useful tool. Complementary to that, we also have LLView, for which you see an exemplary screenshot on the right. LLView is a tool, a web platform for which you get information about all your running and finished jobs, where you can gather all kind of information from simple ones such as did it finish successfully or did it not, to a number of metrics and information and usage that you can use to either monitor, but also to debug and optimize your applications. So besides that, a couple other ones that I want to highlight, but the list of GC tools is very long. One is our in-house developed benchmarking environment that facilitates you running benchmarks and doing scaling on our systems. And then 2 different layer tools that are also developed largely in-house that deal with profiling and tracing, which is Scopy and Scalaska. Also very helpful in order to write better code and make better usage of the compute resources that you can have access to at GSC. But like a lot of these tools are also quite complicated, and you're not left alone just with like being provided all of that. GSC has also an elaborate support infrastructure, so that helps you work with those, but also with all kind of like needs and questions and requests, whatever you would need in order to make the experience as smooth as possible. The first access point, of course, is the general HPC support, and you can contact with any kind of questions you might have. But we also have specific working groups that are of 2 types: ATMLs that are more technology focused. For example, a group that is dealing with performance analysis, another group that is focusing on GPU and porting code to GPU and optimizing GPU code. That on the technology side. On the more scientific side, we have the STLs, which are groups that sit at the intersection between the HPC center and different scientific user communities. For example, we have an STL for astrophysics, one for climate science, and so on. So if you're one of those scientists and you want someone who understands your field, but also to support you or assist you with HPC-related matters, those groups are for that. So, but how to navigate all of this in the best way? There is one kind of point of contact. So if you have a project at any GSC systems, it doesn't matter the type of project. Every project has one project mentor. This is your point of contact. So if you have a need, but you don't really know how to navigate all this landscape, write your project mentor, tell them where you stand, what you would like to have assistance with, and they can connect you with exactly the right working group, recommend you the right tool, possibly help you themselves. And the last thing is also point to the relevant training at GSC, where you can learn how to do various things. So that's about the GSC landscape. Now, Jupyter Booster is almost there. GSC with all that it can provide you there. Now, one of the most relevant questions from a perspective of someone who's running code, from a scientist, is how do I get compute time? How do I get on the machine? So with Jupyter Booster, 50, like there are 2 shares. One share, 50% of that is the national share, which is for either scientists or industry partners who are affiliated with institutions in Germany. This is the national share. Those can apply to so-called GCS calls. GCS is the Gauss Center for Supercomputing, and it's an alliance of the 3 major HPC centers in Germany, out of which GC is one. So the GCS calls are posted in the first link that I shared you. The second one is to the previous GCS call, if you already want to read about how this looks like, because the next one for both regular and large-scale projects, both of which you can apply to Jupyter Booster time, will open on the 7th of July, and it will close on the 11th of August. So this is a time frame to apply for that. Information about the GCS calls you can find in the first link. And then because it's a whole forest of websites, I thought I'll make it a bit easier for you and collected the relevant links on this slide, right? So if you click on the first one, which is the GCS call information, you'll need to scroll down to the important notice on how to apply, click the link, and it will lead you to what I posted you down there. A second access point is not through the GCS website, but through the GSC website, which also posts information about the calls. This is the link below. Both of them ultimately give you access to the fact sheets of the different systems. One of them will be Jupyter Booster. The direct link to this I'll also provide you here on the slides. And in the fact sheet, you will find the actual link to the application. So you need to first go into the PDF of the fact sheet. There you'll have the link, but this is also the link that I posted or like included for you on this slide. So you can click it directly, which leads to you in an interface where you can actually apply for the computer. So that's the national part. Now we come to the European part. So the other 50% of Jupyter Booster are funded and therefore funded by European money and therefore open to European scientists and industry partners to be like more precise. I'll put like the fine print below. So it's research from academia, research institutes, public authorities, and industry established or located in an EU member state or in a country associated with the Horizon 2020. So this is the exact text. It's relevant because that would also include UK and Switzerland, for example, can also apply for this type of resources. So the Euro HPC calls are posted on the website with the link that I provided up there for you. Euro HPC has 5 different types of calls: regular, extreme scale. So these are similar to the ones that also the national part provides. Deadlines are upcoming. So all of them, except for the AI call, are already open. Find them on the website. The deadlines I put you there, for which allocation periods I also put you on the slide. So far, only the extreme scale call, only for that you can get like access to Jupyter Booster. For the other calls, Jupyter Booster will be included in the list of the available system for that call as soon as it's operational. And because it's like not the case at this moment now, but maybe will take another month or so. It's not included yet, but please watch out. And as soon as that's the case, it will be included. You can also apply. So regular and extreme scale are the more or less kind of like regular calls. Next to that, your HPC has also called for development and benchmarking. These are more like preparatory or test accesses. This is why the deadline there is also every month, and you get access to the systems within 2 to 3 weeks time after your application is submitted. For the AI call that is upcoming, they have deadlines approximately every 2 months, and you have a wait time of about 1 month till you get access to the system. So yeah, we are waiting for Jupyter to be fully operational soon and be included in those calls too. If you want to read more about the HPC whole cycle and how it all works for the regular and extreme scale call, I posted a link there into diagram with the time scale and selection steps and everything, and that your proposal goes through. Now a major step, whether you apply for on the national or on the European part, you'll need to write compute proposals. And a major component of a compute proposal is showing that your code can work on, let's say, similar architecture and can scale up, right? So like scaling plots are a crucial information. So how to get this for your applications before actually getting compute time for the first time on such a machine? For that, so for your HPC, this is what development and benchmarking calls are for. This is how you get it there. On the national side, which is, however, also open to the European part, we have something that is called test projects, and how to apply for a test project is linked with the first link. So test projects are on a rolling call basis, so you can apply for this anytime. And with this, you get a fixed, predefined small number of compute time on a system. And you can use this to port your application, to compile it, to make sure it runs, and to produce like first scaling. Duration of a test project is 6 months. And this is what you please should do when crafting or before crafting your proposals for actual compute time. So now Jupyter Booster will be there only in some time. And in the beginning, it still will need to be like tested out properly. Therefore, in preparation for Jupyter Booster proposals, we'd rather recommend that you can apply for a test project on JUWELS Booster, the production predecessor system of Jupyter, and do your testing and scaling plots there. With the experience we gathered with the hardware in terms of GPU compute speed, your applications will be effective to faster on the Jupyter Booster GPUs compared to JUWELS Booster. So you can make your measurements on JUWELS Booster and apply this conversion factor of 2 when calculating how much compute time you would need on the Jupyter system. The second point, however, that is to consider that is that at GSC, the unit of compute time are core hours, and we do not have node sharing. Means if you run your application on one JUWELS Booster node, which has 48 cores, you will be charged, or you need 48 core hours. Independent of whether you used only the GPUs, 4 GPUs, 1 GPU, no GPU, only the CPUs. If you run something on the node, one node, and it has 48 cores, you'll be charged 48 core hours. Jupyter Booster will have 288 cores per node. That means even though both of them have 4 GPUs, right? And you want to compute how much compute time you would need, yes, your code will be 2 times faster. But on the other hand, the unit is core hours, so you need to also make the conversion between 48 core hours and 288. Yes, and please, when you write the proposals, tell us the core hours that you need. Not node, no GPU hours, nothing. That is the GC unit. If you want this to be proofread, cross-checked, helped with, if you have a test project, you have a project mentor, before submitting your proposals, you're very welcome to get in touch with us and get assistance, or just like cross-check whether you did all your calculations correctly. It will facilitate you getting compute time on the systems. So, all right. Besides test project, 2 more things. When you're actually already running compute, doing stuff, and you produce, let's say, a lot of output, or you need a lot of storage to host somewhere your training data sets for AI, GC also complementary has data projects, where you can apply for no compute, but only storage to host things. The call is again rolling call, so you can amend your compute projects at any time with the data projects for extra storage. Okay, so that and the last information, because we're here in Epicure webinar. If you apply through your HPC applications for compute time on Jupyter Booster, as part of the application, you can already indicate that you want to have like extended FAQ support, where they can help you with a number of like more extended topics, like porting your application, looking at its performance, optimizing, debugging, profiling, whatnot. So yes, please note that. All right, so let me see. That's correct. That is it on the infrastructural overview part. In the second part of the seminar, I will hand over to my colleague Jinxian Chu, who will share you his experience running applications on the Jupyter Booster test system that is called JEDI, which was in place here for the early access program, but it will be decommissioned in 1-2 weeks time, and those nodes will be integrated into Jupyter Booster. But it was a great test environment with exactly the same hardware and software stack to gain first experience, and from the perspective of GC, to prepare ourselves to be able to help you when you come on the actual system. So Chu, please, you're welcome now to share all the things that you experienced in the last half year or learned.
All right, thanks so much for your earlier talk. Also, thank you for the succinct introduction to what I'm about to share. So as the name suggests, it's basically a talk on hardware considerations, specifically moving from targeted towards user who is experienced on using x86 architecture like Intel and AMD, and then moving to an ARM architecture, which will be what Jupyter Booster is using because of the GH200 superchip. So I'll go through a few of the topics rather quickly, basically just sharing personal experience on porting codes and which application would that be, but we'll see what happens as the slide goes on. Shall we move on to the next one? All right, just a very quick preview. Yolanta did mention LLView in the slides before, and this is just one of the detailed example of the LLView job report that can be generated, especially on the GH200 superchip architecture. So here is a time plot on the percentage of active streaming multiprocessors on each of the listed GH200 superchip. So here is an example of a job running on 2 nodes. Each node, as you can see on the y-axis of the bottom color plot, you see that each node actually has 4 superchips labeled with the appended number of 00, 01, 02, and 03. So each of the GH200 does have up to 132 streaming multiprocessors, so it can be hard to see if your program is utilizing all of them. So we have LLView just to have a first look whether how active you're using the GPU resources. Yeah, so on to the next one. Next slide, please. Thank you. So aside from this, we also have information on the power measurements. Of course, it's still in active development. We have one of our colleagues who is also present in our current talk itself, who is actually the maintainer and developer of LLView. So if there's any questions specifically on the power measurements and power capping of the superchip on JEDI or soon to be Jupyter, feel free to post your question regarding LLView on that topic, and then hopefully we'll be able to answer those questions. Yeah, so let's move on to a bit of the meat of the topic, which is some of the profiling tools that was mentioned in the prior slides is also available and built on the ARM architecture already. So you won't be able to you don't have to worry whether you have proper debugging tools that's ready to run on the ARM architecture already. So some of those are Linaro Forge, DTTs, Scorpy, TotalView, Valgrind, and the usual suspect for the NVIDIA systems, the NVIDIA Insight and NVIDIA Compute. So those are the multiple profiling tools that you can use in conjunction with others that you might think of, but you have to do a user installation, of course, that you can use to profile your own applications. Right. So next, please. Right. So how easy exactly it is to port existing applications that is traditionally has been running on x86 like Intel and or AMD chips onto an ARM chip. So I'm just going to share a bit of the software management and software module management that we have installed on our systems in JSC. We use the Easybuild management system. So here, good thing about this is that Easybuild framework itself or the GitHub repo itself already includes the ARM-based architecture configurations. So I'm just sharing the GCC toolchain. So of course in Easybuild, you can install multiple toolchains which you can build your own software stack based on the toolchain that you choose. So in this case, I'm just exposing an example for the GCC toolchain. Here, this is a short excerpt of what the configuration inside Easybuild framework does is that when the optimizing architecture arc flag is specified, it automatically injects the -m CPU equals native, which is a specific flag for the compiler on the ARM architecture, so that a subsequent software modules that is built on top of these GCC modules already comes with like proper architectural uh, optimized flag chosen to be built on ARM. So in case your center uses Easybuild or you want to use Easybuild to manage your own software installations and software modules, I think most of the preparatory work has been done already if you choose to use Easybuild. So the given link on the GitHub repo, you can have a look at yourself, specifically for the GCC toolchain. There you'll see the options that has already been default configured. So on the GCC side, it's also rather convenient to move to an ARM architecture, mostly because in GCC's AArch64 commit in September 2022, it made life significantly easier because specifically when you're porting from x86 architecture to ARM, because x86 option usually if you're into optimizing your makefile to compile specifically for the target architecture, most likely you encounter -m arc equals native, which is essentially it's an x86 option which you put into your makefiles that compiles your applications. -m arch equals native is not exactly an accepted option or flag in ARM GCC compiler flag. However, this commit in September 2022 actually in the back end or behind the scene, when it sees this flag, will automatically translate it into -m CPU equals native, and then it will pass on the actual -m arc equals ARM correct version, depending on which hardware you're compiling it on. So this is just an example for GCC where you can say it just works if you use GCC as a compiler. So of course, I've also shared a link where you can look up ARM, especially Architect 64 specific options on GCC compilers when you compile an application on the target architecture. You can refer to it and then tweak your own makefiles as you like. Now, when I say it just works, there's a disclaimer, right? A big disclaimer here is that I've only shown example for the GCC compiler. So there's a lot of compiler out there like NVHPC, Clang, LLVM. So if you are used to using all those different flavors of compilers, please do check the documentation, whether you have to pass in architecture-specific flags that it's provided, etc., before you do the porting. But if you're porting onto our system and then you decide to use GCC toolchain, technically from x86 architecture flag, if you just use March native, it should be fine. All right. Next, please. Now, here we are opening up a bit of a tiny can of worms. Specifically, now we're talking about the GPU aspect, which is the Hopper GPU on the GX200 superchip. So here I put in quote unquote unified memory. It's because the concept of unified memory is already there before the coming of GX200. Now, back then, the unified memory, I think one of the popular NVIDIA posts about unified memory before the coming of GH200 was in 2017, which the unified memory back then is actually done via the call of CUDA malloc managed. Now, with the coming of GH200, with the NVLink C2C, there comes a point where you can actually just do a malloc call, and then the back end is going to automatically handle the memory migration from CPU page table to GPU page table, etc., etc. Now, the subsequent slides from here onwards, it's only for people who want to develop code specifically on GH200's unified memory, right? Your explicit memory copy CUDA code that you've developed for the past 10 years, it still works on hardware. So this is only for people who wants to experiment without having to do with explicit copies anymore. All right. So I've also cited a paper down here, which is very informative and quite illuminating if you're interested to look at, okay, what are the caveats between system allocated memory and managed memory on GX200? So I'm going to share a bit of the takeaways from the paper in the subsequent slides. But don't be afraid that you have to adapt your code. Your old code with explicit mem copies still work on GH200. Right, next please. Now, of course, the concept of first touch is already like there also in CPU considerations. It's just that here there's a clear distinction between first touch by CPU or first touch by GPU. Right. So just to recap, for those who might not have heard of it, first touch policy is basically a memory page. Basically, when you call a malloc function, it is actually not allocated. The memory is not actually allocated, but actually is on first access. So in the case of GH200, what this means is you have a choice to choose either malloc or CUDA malloc managed. If you use malloc specifically and then use GPU kernel calling the allocated memory, it is classified as system allocated memory. If you do CUDA malloc managed, it is classified as managed memory. Okay, so system allocated memory, actually all the memory allocated page, they are all placed in the system page table. System page table is not so accurate wording, but suffice for now is the CPU side of the page table management, right? So regardless if you call malloc, regardless if you do GPU first touch or you call CPU first touch, it will always be managed by the system page table. Okay. If you choose to do CUDA malloc managed, then it always places it will place the allocated memory page into either CPU page table, which is the system page table, or the GPU page table, depending if you access the allocated variable on GPU first or CPU first. Just for completeness, what I mean by access or first touch here is more like who calls the definition, that's not a definition, who calls the assignment of value into the variable first? Is it done on GPU or is it done on CPU? Okay, so the other thing that is also quite important to keep in mind is that the access granularity between the two memory type is also different. System allocated memory, again, just to rehash, is the malloc function, is accessed at the granularity of a cache line, which is in the order of tens of bytes, usually 64, or could be small. For the managed memory access is usually at the granularity of page size, which is kilobytes in orders. So common numbers would be like 4 kilobytes, for example. So in actuality of, let's say, running your code on GH200, if you choose to use system or managed memory that does not require explicit CUDA mem copy, these 4 points apply. Now, let's say if you use malloc and you do first touch on the GPU, that you assign variable values in the GPU kernels, it would be slow to initialize, mostly because, as I've mentioned in the first point up there, system allocated memory always places the page in the system page table. Meaning, if you assign variable values in GPU kernel in a system allocated memory which is using malloc, the GPU actually communicates a page fault, and the CPU has to then take over and handle the page fault, and then places the memory page in the system page table, and then going back to the GPU so that the GPU can work with the memory. So this is why if you use malloc, if you initialize the value in the GPU kernel, it takes a performance hit. In the managed memory case, however, if the first touch is done by GPU and you expect that all the computation is done on the GPU without CPU's involvement, the allocated page directly is placed into the GPU page table. Good performance. There's no need to communicate between host and device. Everything's good. Okay. Now, in the other scenario where, back to the system allocated memory using malloc, if the first touch is done by a CPU, of course, initialization of the variable is faster because, again, the page is always in the system page table. The good thing about small excess granularity of a cache line using a system allocated memory is that as the GPU does the computation and takes, let's say, memory from the CPU page table, it doesn't suffer as much impact as you're doing a page size memory transfer because it's just a cache line of multiple, like tens of bytes. So the spread of the cost of access is going to be much, let's say, more manageable. So in managed memory, however, the first touch, if you do the first touch is done by CPU, where the page is put on the system page table, you pay an upfront cost of access to move a page size access onto the GPU. However, I would say it's not really however, but actually a positive side of that is you pay the initial transfer cost. And then if the computation all happens on the GPU side, it doesn't incur the cost of like transferring anymore. So there's no transfer cost happening for managed memory if you've already moved the pages onto the GPU page table. So choosing which memory type to use, either system allocated memory or managed memory, it highly depends on what you expect your program flow to be, right? So not to say that one is definitely better than the other. It depends on what is the number of page fault you expect, whether your whole problem fits entirely on the GPU, or do you have to do host to device copies, etc. Okay, so I hope it's clear. I hope I'm not confusing anyone here. All right, next page, please. So, takeaway message. It seems all too complicated, but if you're not interested in adapting your code to utilize the latest and greatest unified memory on the GH200, it's all fine. Existing CUDA code with explicit copy still works. It's just a heads up for people who like maybe already uses CUDA malloc managed on older GPU versions, then yeah, this will be something you need to worry about. Okay. Because CUDA malloc managed exists like way before GH200 exists. So the semantics and how the hardware handles CUDA malloc managed is different on the Hopper, and it's also different on the GH200, right? So please, for those people, please, I recommend you to read the paper that I've like shared the link to here. Okay. Of course, this is a very simplified overview. There's always like prefetching and things like that. For the sake of time, I'm not going to get into it. I'm realizing we only have 5-6 minutes left. So I'm going to run through the last of the slides. Next, right. Okay. ARM memory. ARM hardware architecture. I don't really have much time to go into it. And also one need to be aware of, this is a very high level discussion. Some of the wordings is not by literal definition accurate. It's just enough for you to have a hook and actually do further reading yourself. Things to note, x86 is what is classified as a strong memory ordering model. ARM is a weak memory ordering model. Next slide. I'm actively deciding what to go into, what not to, because if I go into something, it's going to be like a lot of explanation. Right. What does it mean by strong memory ordering model? These are the 8 points that is codified by Intel compiler engineers not compiler engineers, but hardware engineers in conjunction with like experience working with software compiler engineers. So just to illustrate the point, the first 4 points are the ordering of the program instructions. So compiler, what it does is you write a code on, let's say, C++, Fortran, whatever. Compiler is going to translate those code into assembly instructions. The assembly instructions is still considered to be software level memory models. Now, software memory models have already converged into what they call sequential consistency with data arrays free, what they call a model, which is SCDRF. Now, that's the software side. Now, how does the hardware interpret and actually operates on the generated assembly instruction? There is additional restriction based on the hardware architecture design itself. x86 is considered a strong memory ordering model because if the hardware processes and it sees sequential loads, one after the other, during the execution of it on the hardware level, it's not going to automatically reorder it for the sake of optimizing memory access. So you have a really good software performance. It's also not going to reorder stores. Loads are operations which is like reading or accessing a variable. Stores are writing to a variable, right, into the memory, right? So loads are not reordered with loads. Stores are not reordered with stores. Stores are not reordered with older loads. And some people might think, wow, this is a lot of restriction. Thus, therefore, the code might run slower on a strong memory ordering model. However, it is closer to what ideally sequential consistency is. So therefore, you have a larger guarantee that your code runs exactly as how you imagined it to run. Now, moving on, next slide. On the ARM architecture, it is a weak memory ordering model. I took this from the ARM developer webpage itself, which here on the left side is the generated assembly instructions from the compilers. And here we have the first is the writing to a variable, a store operation, store register. And then the following two is load register, which is like what you can interpret as reading the value of a variable. So we have access 1, 2, and 3 in sequence in the generated assembly instruction. Now on the hardware execution side, look at the bottom 3. Actually, it completes access 3 first and then returns access 2. So ARM allows reordering of load orders, which is something that is not allowed on x86. So moving forward, yada, yada, yada. Generally, things should all be fine because we trust that the compiler engineers knows what they're doing with the architectural instruction set that are given by our hardware designers. They know how to compile, they know how to convert code into proper assembly instructions, and therefore also like trust that the hardware handles it properly. Generally, it's all fine because the folks at the compiler engineers and hardware architecture people, they're all smart people. This is something that you don't need to worry about, except for maybe some edge cases, right? Relax atomics. Okay, I'm not going to start a topic. It's going to go on and on. So best practice, moving from x86 to ARM always would be ideally benchmark the results between the architectures, especially for highly optimized code, with a lot of like optimization, like relax atomics, mutexes, etc., etc. Make sure it produces the right results, and there's no like funky memory operations that you didn't expect it to happen. Then you can be sure that your program runs correctly on ARM. I think that's the last slide. Next slide. All right. This is my application. General performance is the application is a plasma simulation specifically capturing plasma microturbulences in tokamak device nuclear fusion devices. This is basically the takeaway. If this code is already fully ported to run on GPU entirely. So if your code is running entirely on GPU, what you can expect is generally a 2x speed up compared to A100 GPUs. So the graph basically shows the top of the graph, the number 8, 16, 32, 64, is the number of nodes that we run on Eureka DC on the same problem size of 200 times 128 times 96 times 70 times 24 grid points. On the bottom of the graph is the number 4, 8, 16, and 32. And a skilled observer among you would have known that this is running twice the number of GPUs on Eureka DC nodes compared to the JEDI node. And each Eureka DC node has 4 A100s, each of the JEDI node has 4 GH200 superchips. Now, what this means is if the line is close to each other on top of each other, it is exactly 2x speed up on the GH200 superchip. But it is a bit lower than the Eureka DC like timing. So it means it's a little bit faster than 2x speed up on the GH200 superchip compared to A100. So therefore, Yolanta previously shared in the earlier slide is that, right, do your test on your JUWELS Booster. If your code is purely GPU only, you can expect a factor 2 speed up on the GH200. Right. I think that's it. Can you check the next slide for me? Yeah, okay, these are all the takeaway message you can read on yourself. I've tried my best to be concise, not exactly wordingly accurate, but enough that it conveys the general 80% of the message. Right. There are links on appropriate places where you can actually read up on yourself. Yeah, I believe that's it. Thank you and sorry for going over 2 minutes.
Yeah, thanks a lot. It's just such a treasure chest of knowledge that you have gathered over the last half year. So thanks. I will still leave the slides on for the questions. Therefore, if someone else might navigate us through the questions, so I can go to the respective slides.
Yes, so we have two questions in the chat. So the first one is it possible to get access to a demonstrator before Jupyter is available on development and benchmark calls of your HPC?
What do you mean demonstrator?
So I guess it's to get early testing for Jupyter.
So from the Euro HPC side, the benchmarking and development calls are those like early preparatory
No,
test.
but before Jupyter is available for development and benchmark.
I mean, before Jupyter is available, you have the test projects at GSC, but then on other systems like JUWELS Booster, not Jupyter Booster, but JUWELS Booster. I mean, while Jupyter is not there, I mean, you can't get there. So, but you can apply for a test project on JUWELS Booster and write in why you need that as like you want to already port your applications on one of the GC systems and yeah, test performance for a proposal for Jupyter.
Okay, and the other question is there an automatic page migration from CPU to GPU memory for system allocated memory?
Yeah, from what I read from the paper, there is. Uh, I'm just not exactly sure how does it compare performance-wise. I'm not even sure if it's like page migration directly. Mm, yeah, because the granularity of the access is cache line. I suppose prefetch should still work in this case, but I need to check. This is something that I've never thought about at the moment. I'm sorry, I can't give you a more concise answer. Yeah.
So, anyone in the audience want to ask any question? So, if not, let's thank our speakers. It was a very nice talk. Thank you very much. Uh, and we hope to see you all in the future Epicure webinars, uh, and which will be announced uh, as soon as we have a certain date for a new one. So, well, thank you very much once again, and yeah, have a nice day.
Thanks a lot.
Thank you.
Bye bye.